Okay, Algebra. So today we're looking at Unit 7, Lesson 1 on quadratic scatter plots. Our aim is, given a scatter plot, students will be able to recognize data that is best modeled by quadratic functions. Our Think About It says, in the United States, most children with HIV infections receive the infection from their mother when they are being delivered. This transmission is known as mother-to-child or perinatal transmission. In the 1990s, infections transmitted from mother to child in the United States were greatly reduced, in part because of the use of the drugs such as zidovudine. Part A says, examine data in scatter plot provided and use your graphing calculator to model this data with a linear and exponential regression. Remember that the word regression is just referring to the relationship between our variables. In this case, our variables are the years and the number of cases of HIV. So because we probably don't have a graphing calculator at home, let's just look at the general shape of our data. A linear regression would have a constant rate of change, with the graph looking similar to a straight line. An exponential regression would have an increasing or decreasing rate of change, with our graph looking like our exponential function, where we start low and increasingly grow faster. Based on the data and the scatter plot that we have, does a linear or an exponential regression represent the data that we have? Not really. When we're looking at our data, we can see that it's increasing, and then at some point between 1990 and 1993, it changes and our data points start going down. This means that our rate of change is not constant. At one point, it's positive and increasing, and then at another point, it's decreasing. So we know that a linear or an exponential regression will not represent this data. You guys can use that information to fill out Part C on your own. So what is our big idea for today? Well, we know linear regressions and exponential regressions. We've been over that previously. Today, we're going to be introducing quadratic regressions. A quadratic regression represents data that has a changing sign of the rate of change. When I'm talking about a changing sign, I'm saying that at one point, my rate of change is positive, meaning it's increasing, and at another rate, it's going down, it's decreasing. Now that we know our big idea, let's go ahead and move on into our interaction with new material. Example 1 says, complete the following questions using the data from the Think About It problem. Part A says, using the same data from the Think About It, complete a quadratic regression and record the equation and correlation coefficient. Need to enter our data. So I'm going to go to hit stat and edit, and I can see that I've inserted all of the data from our table. So now I can go to calc and hit 5, which will give me my quadratic regression. When I type that into my calculator, I get all the information that I need in order to write my equation. So I can write my equation as negative 12.68x squared plus 167.33x plus 222.21 is equal
to y.
So I have my equation written out using the information from my calculator. So now let's look at part B. Explain what is different about the form of the equation versus other functions we have worked with this year. So again, the three main functions that we have are linear, exponential, and quadratic. We know that for a linear equation, we're typically in the form y equals mx plus b with a constant rate of change in our graph as a straight line. I have an exponential function. I typically have f of x is equal to b times a to the x power. We have an increasing or decreasing rate of change, meaning it's not constant, and that our graph is that curve that we know. For a quadratic function, we're typically in the form y equals ax squared plus bx plus c, so our standard quadratic form, with a rate of change that has a changing sign, meaning again, part of my rate of change is positive, and the other part of my graph has a rate of change that's negative. What do we notice about the variable in each of our functions? We can tell that in a linear function, our variable has no exponent. I just have x by itself multiplied by our slope. In an exponential function, I can see that my variable is the exponent. I have a to the x power. And in a quadratic function, I can see that the variable has the exponent of 2. So I have x to the second power. So how the variable is different in each of the functions relates to how the rate of change is different between each of the graphs. So now let's look at part C. Describe in one sentence the relationship between the number of cases of HIV infections in the US in years since 1985. So let's look at our chart. We can see that obviously our data points are increasing and going up from the beginning. And then there's some point in between here, between 1990 and 1993, that something happens, because at 1993 and moving forward, our data points are increasing. So again, we have an increase starting from 1985, and then a decrease after 1993. What is the relationship between the number of cases of HIV infections and the year since 1985? You can say that the number of cases of HIV are increasing starting from 1985, and then sometime between 1990 and 1993, cases begin to decrease. Again, we don't know the exact date that the cases begin to decrease because we do have this 3-year gap in between. So we can just say sometime between 1990 and 1993. Moving into part D, it says the use of drugs such as SWBAT was emphasized by this initiative. Based on the graph of the US data, do you think it was a good idea? Explain by citing data from the graph or table. So this question you guys need to do on your own, recognizing if our number of cases of HIV were increasing, then they introduce a drug and our cases begin to decrease. Was it a good idea? You guys can use specific data points and answer letter D on your own.